Hey guys, this is going to be your 4.5 lecture. So in 4.5, we're talking about two things. We're talking about indeterminates form, and we're getting a new rule called L'Hopital's rule. Now these are both concepts involving limits, and specifically indeterminate forms are forms where we get something that, well, we can't determine what's going on. So if we take the limit of some stuff as x approaches, you can pick anything you want. I'm going to say 0 here just for fun. And you would, if you try to evaluate it by direct substitution, you get something like 0 over 0, or infinity minus infinity, or infinity over infinity. These are all indeterminate forms. One more, 0 times infinity. So we don't know what's going on with that. For instance, say the limit as x approaches 0 of x e to the x. Now that's an indeterminate form because if I were to, no it's not, sorry. Let me say that better, x e to the 1 over x. So now as x goes to 0, that would be something like 0 times e to the 1 over x will be something like e to the infinity. So that'd be a 0 times infinity kind of a case. So we're not saying it's equal to 0 times infinity. We're describing how that limit doesn't have a nice form by saying it would be a 0 times infinity case. Another one, and this one's familiar to us, is sine x over x. Now we learned back in chapter 2 that this limit is 1. And so these limits can exist or not exist, but this is still an indeterminate form because if you directly substituted in for 0 for x, you would get a 0 over 0 case. What L'Hopital's rule is a way to handle specifically the 0 over 0 indeterminate forms. So for instance, this one here. So we know it's supposed to be equal to 1. If you'll recall, I used a sandwich theorem argument to show that it was, and everybody kind of scratched their head for a minute. So in a second, I'm going to use L'Hopital's rule on it, but let me give you L'Hopital's rule first. So if you have f of a equals g of a equals 0, and f and g are differentiable on an interval, an open interval, containing a, and g prime of x is not equal to 0 on that same interval, except at a. We'll call that open interval I. Then the limit as x approaches a of f of x over g of x can be found. This is L'Hopital's rule here. This limit can be found by taking the limit as x approaches a of their derivatives. That's pretty straightforward. It's maybe not obvious that that's the case, but you can see why some of these conditions are necessary. F and g had to be differentiable because we're going to take their derivatives. G can't be equal to 0 except at the limiting value of a, because we're going to divide by it. And specifically here, f of a equals g of a equals 0 puts us in that 0 over 0 indeterminate form. And L'Hopital's rule is great for 0 over 0 indeterminate forms. So let's go back to that kind of classic problem there. So the limit as x approaches 0 of sine x over x, which we know should be 1 because you trust me, maybe. Now, sine of 0 is 0. 0 is 0, so it's a 0 over 0 indeterminate form. So we can use L'Hopital's rule and say this is equal to the limit as x approaches 0 of cosine x over 1. Well, that's really easy because now it's not indeterminate at all. As x goes to 0, cosine will go to 1, and this is just 1 over 1, which is the promised 1. That's way easier than the sandwich theorem argument we made back in the day. Let's do another couple of examples here. What if we take the limit as x approaches 0 of root 1 plus x minus 1 over x? So let's check to see that we're in the right kind of indeterminate form. One of the things that, that we'll do to trick you with L'Hopital's rule is give you a limit that you could have just done some other way. L'Hopital's rule, the taking the derivative thing, only works if it's a 0 over 0 indeterminate form. So if we plug in x equals 0, we get root 1, which is 1 minus 1. So the numerator would be 0, and the denominator would also be 0. So it is eligible for L'Hopital's rule. And so L'Hopital's rule says that we can take the derivative of the numerator and of the denominator. And you can see why taking the limit of that denominator is useful. So the limit of the numerator here is going to be 1 over 2 root 1 plus x, and then minus 0. So this is equal to the limit as x goes to 0 of 1 over 2 root 1 plus x. And as x goes to 0, that's going to be equal to 1/2. Let's see what else we can do. How about the limit as x goes to 0 of x minus sine x over x cubed? Now there we don't know what the limit of sine x over x cubed is. We could split that into two limits pretty easily and write that as 1 over x squared minus sine x over x cubed, but we would still have a 0 over 0 indeterminate form in there. Double check to make sure we have one to start with. We have 0 minus 0 over 0. So yeah, we've got a 0 over 0 indeterminate form. So we'll use L'Hopital's rule, take the limit still as x approaches 0. That's going to be popular here because we're going to want our numerator and denominator to be going to 0. And so we're going to take the derivative, so that'll be 1 minus cosine x over 3x squared. Now it's important to note here that you can't just take L'Hopital's rule again. Sometimes it is useful to take L'Hopital's rule twice, but before you take it a second time, I'm sorry, I should have told you, this is one of those cases where we're going to see, oh, that's still a 0 over 0 indeterminate form, 1 minus 1 over 0. So we can take L'Hopital's rule again, but as soon as you learn that you can take it a second time, you'll have a tendency to keep using it past the point that you should. So watch very carefully and make sure you only ever use it if you have a 0 over 0 indeterminate form. So this would be minus sine x over 6x. Now that's another indeterminate form. And I'm going to go ahead and use L'Hopital's rule again. If you remember sine x over x is 1, you're going to see that's negative 1/6. But, you know, we're in the L'Hopital rule section, so let's use it 3 times in one problem just for fun. So this will be the limit as x approaches 0 of minus cosine x over, hold on, quick mistake. Derivative of negative cosine should have been positive sine. So that should be positive cosine. Still 0 over 0 indeterminate form, because we get a plus sign there, over 6. Now that is not a 0 over 0 indeterminate form, and we can take this limit by direct substitution and get 1/6. How about a couple of one-sided limits here? So let's take the limit as x approaches 0 from the right of sine x over x squared. Definitely an indeterminate form, so we can use L'Hopital's rule. Sorry, a 0 over 0 indeterminate form. L'Hopital's rule tells us that's going to be the limit as x goes to 0 of cosine x over 2x. Now that is not a 0 over 0 indeterminate form. Cosine is never bigger than 1, and near 0, it gets as close to 1 as you would like. So this is like 1 over 0. We are taking the limit from the right, so as x approaches 0 from the right, cosine is still going to go to 1, and 2x is going to go to, well, 0 from the right, so that's going to be equal to positive infinity. But if we take the limit as x approaches 0 from the left of sine x over x squared, then that's the limit as x approaches 0 from the left, again using L'Hopital's rule. So that'll be cosine x over 2x. So nothing changes here except now that we're approaching 0 from the left. Cosine is still going to 1, but now the denominator is going to 0 from the left, so the whole thing will be going to negative infinity. So we can even use L'Hopital's rule to show that the limit didn't exist. That's what happens in this case. The limit of sine x over x squared doesn't exist. Sometimes we can write something in a nicer way. So L'Hopital's rule applies to 0 over 0 calculations. We can also use it for infinity over infinity indeterminate forms. We just have to be careful. So just as an example here, one way you can do that is by taking the reciprocal often. So if I had something like the limit as x goes to infinity of no, that's not helpful. I'm sorry, that's a bad example. Maybe I'll have one in a minute that's a better example. Let's work this one instead. Let's take the limit as x approaches infinity of natural log x over 2 root x. So the natural log of infinity is infinity, and square root of infinity is still infinity. So this is an infinity over infinity indeterminate form. And we can apply there's only one way to approach infinity. So we can think of it as approaching infinity from the left if you need to. Sometimes that matters with infinity over infinity indeterminate forms. It won't on this one. So using L'Hopital's rule, we're going to take the limit as x goes to infinity, and then we're going to take the derivative of the numerator, that's 1 over x, and the derivative of the denominator is 1 over 2 root x, but we had a 2 there already, so we get 1 over root x. Little cleanup there. That'll be equal to the limit as x goes to infinity of root x over x, which is equal to the limit as x goes to infinity, just simplifying, that's 1 over root x, which is going to be 0. But if we were to have something like the limit as x approaches pi over 2 of secant x over 1 plus tangent x. So as x goes to pi over 2, secant is undefined and tangent is -1. No, that's not right. See, no, tangent is undefined at pi over 2 because cosine is 0 there. So we end up with an infinity over infinity case, but depending on which way this is going, we'll need, like, whether we're looking at the limit from the left or the right will determine whether these are positive or negative infinity. So let's take the limit as x approaches pi over 2 from the left. So then of secant x over 1 plus tangent x. So now as we approach from the left, we're in the first quadrant. And in the first quadrant, everything is positive. So secant is positive, tangent is positive. So this is an infinity over infinity indeterminate form. And we can use L'Hopital's rule here. Still taking the limit from the left, take the derivative of secant, and we get secant x tangent x. Take the derivative of 1 plus tangent x, and we get secant squared x. So a little simplification there using our trig functions. That's the limit as x approaches pi over 2 from the left. We will get, let's see, tangent is sine, let's just write it out. So that's going to be sine x, and then the secant x puts a cosine x downstairs, and then another one from the tangent x, and then this puts a cosine squared up top, so those all cancel, and we get the limit as x approaches pi over 2 from the left of sine x, which is 1. Now technically, we need to go ahead and check the limit as x approaches pi over 2 from the right of secant x over 1 plus tangent x. But applying L'Hopital's rule here, we're going to get the same thing. We're going to get, once we've applied L'Hopital's rule, it actually doesn't depend on the side, right? We're going to get the limit as x approaches pi over 2 from the right of sine x, which isn't going to plus or minus infinity there, so we still get a 1. And so some of these infinity over infinity indeterminate forms will be like this, where you get the limit from the left equals the limit from the right, so they're equal, and you can do them both using L'Hopital's rule. But sometimes you'll get a different limit from different directions. So L'Hopital's rule doesn't make limits exist where they didn't before. It just lets us find them if they can be found. For instance, if we take the limit as x approaches infinity of e to the x over x squared, we're approaching positive infinity from the left, so everything here is positive. So when we use L'Hopital's rule, we get the limit as x approaches infinity of e to the x over 2x. And we might as well go ahead and do that again. Take the limit as x approaches infinity, take the derivative of the numerator and the denominator, get e to the x over 2. Again, that was just another application of L'Hopital's rule. Now the numerator is going to infinity, the denominator is constant, so the limit doesn't exist in an infinite way, or the limit equals positive infinity, if you'd rather say that. Now, one of the other indeterminate forms is 0 times infinity, or infinity minus infinity. Sometimes we can do something to change them into an indeterminate form that we can do something with. So for instance, the limit as x approaches infinity of x times sine 1 over x is an 0 times infinity, or really an infinity times 0 indeterminate form. And we can't write that, we can't use L'Hopital's rule on it directly. This was what I was talking about a moment ago when I said sometimes you can rewrite them using a reciprocal. So we can say the limit as x goes to infinity of sine 1 over x over 1 over x. Those are equal. And now that is 0 over 0 indeterminate form. So we can use L'Hopital and take the derivative of the numerator and the denominator, and they will be equal in limit. So that would be cosine 1 over x times negative 1 over x squared over negative 1 over x squared. So those will cancel, and I get the limit as x goes to infinity of just cosine 1 over x, which is 1. So what else can we do with this? Well, there's a different kind of, infinity minus infinity, almost forgot. So in infinity minus infinity case, this would be like the limit as x approaches 0 of 1 over sine x minus 1 over x. So that would be, if we did that by direct substitution, that would be infinity minus infinity. So in this case, sorry, I said infinity minus infinity. Yeah, that's right. If I get a common denominator, that's the limit as x approaches 0 of, my denominator will be x sine x, which will be going to 0, and my numerator will be x minus sine x, which will also be going to 0. So just by getting a common denominator, I now have a 0 over 0 indeterminate form. And then L'Hopital comes into play, and I can take the derivative of the numerator and denominator and get the same limit. So I get 1 minus cosine x, and I get x cosine x plus sine x. So double check, as x goes to 0, I've still got a 0 over 0, so let me do L'Hopital one more time. That'll be the limit as x goes to 0 of negative sine x, positive sine x, almost fell for it again. That'll be x sine x plus cosine x plus cosine x. So as x goes to 0, this will be equal to 0 over 0 plus 1, which is 0. So all of our indeterminate forms, if we're kind of a little bit clever, at least most of the time, we can rewrite them in terms of a 0 over 0 or an infinity over infinity. we can do some other things too. We have a property that says if the limit, that's a weird if, try that again. If the limit as x approaches a of the natural log of f of x equals L, then the limit as x approaches a of f of x equals e to the L. Essentially what's happening here is we can pass the natural log through a limit, or we can pass an exponential through a limit. This happens because they're continuous operators and they work very nicely. But this allows us to handle another kind of indeterminate form, like what is 1 to the infinity? Like we know literally if it's the number 1 to infinity that that's equal to 1. But, so the limit of 1 to the n as n goes to the infinity would be 1. But what if it's something very close to 1? What if it's approaching 1 over infinity? Then it gets weird. 0 to the 0 is weird. So usually anything to the 0 power is 1, but usually 0 to any power is 0. So which one of those guys is going to win? And similarly, infinity to the 0 is weird because infinity to any power is infinity, or 0 if it's a negative power, and anything to the 0 is 1. So those leave us in some weird cases. So those are some different indeterminate forms. Our book calls them indeterminate powers. And essentially, we can use this property to bring our powers down. As an example, let's see, what do we have? So let's take the limit as x approaches 0 from the right of 1 plus x to the 1 over x. So if you look at this, this is approaching 1, that is approaching infinity. So that's a 1 to the infinity indeterminate form. And we can't use L'Hopital's rule, but we know that if we want to call this f of x, that we can find that limit by finding the limit as x approaches 0 from the right of the natural log of 1 plus x to the 1 over x. It's not the same. These are not the same. But I can find this first and then raise it as the exponent of e in order to find the answer to this case. Now that looks like I was dividing by f of x. So this is my f of x, so then this is the limit of the natural log of f of x. And so then in the end, we can find the limit of f of x. All right, the reason for using the natural log here is that this can be written as the limit as x approaches 0 from the right of 1 over x times the natural log of 1 plus x using our logarithmic properties. Now as x goes to 0, that's going to 0, and the x is going to 0. So if I just write it like this, I have a 0 over 0 indeterminate form again. So now we can use L'Hopital's rule to take the limit of this function, and that's going to be 1 over 1 plus x over 1. So that is just 1. So the limit of the natural log of f of x as x approaches 0 from the right equals 1. This says then the property that we had on the previous page, that the limit as x goes to 0 from the right of f of x is equal to e to the 1, or just e. All right, so I am not going to prove L'Hopital's rule, and you will not need to know Cauchy's mean value theorem. So that concludes the lecture on 4.5.